I draw an illustration of the accelerometer. Inside the accelerometer, there is a ball hanging on a spring. When the accelerometer is stationary, the reading is 1G. It's like this. Here is 1G. Here is 0G. Here 2G. Here 3G. Here 4G. When the accelerometer is stationary, the FBD of the ball inside the accelerometer is like this. This is the ball. This is the gravity on the ball. This is the pulling force of the spring on the ball. When the accelerometer is stationary, the sum force on the ball is 0. That is sigma F equals 0. So the pulling force of the spring on the ball minus the gravity of the ball equals 0. So the pulling force of the spring on the ball equals the gravity of the ball equals mg. M is the mass of the ball. Now the reading of the accelerometer is 1G. That means when the pulling force of the spring on the ball is mg, the reading on the accelerometer is 1G. So when the ball is at 2G, the pulling force of the spring on the ball should be 2mg. When the ball is at 3G, the pulling force of the spring on the ball should be 3mg. For this accelerometer to work, the spring should extend. Then we can get reading on the accelerometer. That means to use this accelerometer, the top end of it should point to the direction of the acceleration. In this way, the spring will pull the ball, give it a pulling force. The pulling force will generate the acceleration of the ball. When the spring pulls the ball also pulls the spring, and the spring will extend. Now, I do question A. When the person is at the top of the loop, there are two forces on the person. One is the gravity, Fg. Another one is the pushing force of the seat on the person, Fa. The question said, you experience a force of 2 times your normal weight from your seat. That means the force Fa equals 2Fg equals, so the sum force on the person is sigma F equals Fg plus Fa equals 3mg. The acceleration of the person is acceleration equals sigma F over m. M is the mass of the person, so equals 3mg over m equals 3g. We know that acceleration equals speed square over radius r. So speed v equals square root ar equals square root 3GR equals square root 3, 9.8. The radius is 18. So at last, the speed v equals 23 meter per second. Now see question B. It asks, identify the forces acting on the accelerometer. So at the top of the loop, the accelerometer should be like this way. Because when being at the top of the loop, the direction of the acceleration points down. So this end of the accelerometer should also point down. So the forces on the whole accelerometer should be, so this is the whole accelerometer. There should be two forces on the accelerometer. One is the gravity on it. Another one is the pulling force of the person on it, because the person holds the accelerometer. At the top of the loop, there should also be two forces on the ball inside the accelerometer. One is also the gravity of the ball. Another one is the pulling force of the spring on the ball. These two FBD seems similar, but one is for the whole accelerometer, one is for the ball inside the accelerometer. So now let's go to question C. Question C asks, what reading will you observe at the top of the loop? If the accelerometer is calibrated as in figure 3, as described before, at the top of the loop, there are two forces on the ball inside the accelerometer. One is the gravity on the ball, another one is the pulling force of the spring on the ball. So the sum of force sigma m on the ball at the top of the loop should equal to gravity plus the pulling force of the spring on the ball. And also we know that at the top of the loop, the acceleration equals 3g. Sigma f also equals to the mass of the ball multiply the ball's acceleration equals 3mg. So we know Fg plus Fa equals 3mg. Fg equals mg plus Fa equals 3mg. So Fa equals 2mg. We analyzed before. When the pulling force of the spring on the ball is 2mg, the reading on the accelerometer should be 2g. So the answer for question C should be 2g. My answer is different from the textbook. The answer on the textbook is 3g, not 2g. But I think the answer on the textbook is wrong. This is just what I think. If you don't agree with me, please leave your comment and tell me your reason. Thank you. Now for question D. It asks, what likely sources of error would you expect? As described before, when using this accelerometer, the spring end of it should point to the direction of the acceleration. So if you does not position the accelerometer in the right direction, the error will be introduced. For example, at the top of the loop, the position of the accelerometer should be like this way. If you put it in this way, you won't get the right measurement.